So in today's session, let us start with sensitivity of Wheatstone bridge. So far we had covered balance condition of Wheatstone bridge. We had seen Wheatstone bridge under slight imbalance, and we had also seen expression when the bridge arms were equal. In today's session, let us continue with sensitivity of Wheatstone bridge. So as per the definition, sensitivity of Wheatstone bridge is nothing but deflection of the galvanometer per unit fractional change in the unknown resistance of the bridge. So bridge sensitivity is denoted by S subscript B. So SB is equal to theta divided by delta R by R, where theta is the deflection of the galvanometer, delta R is the incremental resistance, capital R is the unknown resistance, and SB is the bridge sensitivity. So a small change in the deflection, a small change in the galvanometer deflection for a small change in resistance is nothing but sensitivity of Wheatstone bridge. And this bridge sensitivity depends upon sensitivity of the instrument galvanometer itself. Next, if we want to define this bridge sensitivity in terms of voltage sensitivity, it can be done, which is SV, which is a voltage sensitivity, is given by ratio of theta by E, where theta is nothing but the deflection, E is nothing but applied voltage. It is defined as the amount of deflection per unit voltage applied to the galvanometer. And bridge sensitivity in terms of voltage sensitivity is nothing but SB is equal to SVE divided by delta R by R, where this R, capital R, is nothing but R4 in your circuit. E is the applied voltage. So already we have derived the expression for E. So let us just substitute for that here. So you'll have SV into E into R3 delta R R4 divided by R3 plus R4 the whole square multiplied by delta R. So this, if you rearrange, you have SB is equal to SV into E into R3 R4 divided by R3 plus R4 the whole square. So this is the expression for bridge sensitivity in terms of voltage sensitivity. So I hope this expression is clear. SB is equal to SV into E by delta R by R. E is the applied voltage, which is nothing but your VTH. We are substituting the expression for VTH that we had got in the earlier derivation. So if that is substituted, you'll be getting SVE into R3 delta R R4 divided by R3 plus R4 whole square into delta R. Delta R gets cancelled. You will be left out with SVE R3 R4 by R3 plus R4 whole square. Next, we try to get an expression for maximum sensitivity of the bridge. When can the bridge sensitivity be maximum? That's what we are going to check here. So we are rewriting the same expression that we had got in the previous step. SB is equal to SV into E into R3 R4 by R3 plus R4 whole square is expanded here. R3 square plus R4 square plus twice R3 R4. Now in the denominator, let us divide all the terms of the denominator by R4, so that you have SVE divided by R3 by R4 plus R4 by R3 plus 2. So once that is done, so what we have done here is divided the entire denominator by R3 R4, or we have transferred this R3 R4 from the numerator into the denominator. So we are left out with SVE divided by R3 by R4 plus R4 by R3 plus 2. So from this we can see that whenever R3 by R4 ratio is equal to 1, this particular SB can be maximum. Mathematically you can observe that whenever R3 by R4 is 1, in the denominator it will become 4, and SB will be equal to SVE divided by 4. That is the condition where any other value of R3 by R4 other than 1 will not give you the maximum value. Under this condition, SB will be maximum, so we have called it as SB maximum, which is equal to SV into E divided by 4. Next, we can also define SB in terms of current sensitivity. So that is given by SI is equal to theta divided by IG. So it is defined as amount of deflection per unit change in current through the galvanometer. So the deflection that you are going to observe for a small change in current is nothing but bridge sensitivity in terms of current sensitivity. So SV is equal to SI divided by R equivalent plus RG. So we already have the expression for the same. So we know the expression for SI. So we are going to substitute for, sorry, we have the expression for SV. We are going to substitute for SV. So you have SI into E into R3 R4 divided by R equivalent plus RG into R3 plus R4 whole square. We were just substituting the other expression over here. So you can have a look at the first expression. SB is SV into E R3 R4 by R3 plus R4 whole square in A. So that itself was being substituted over here in order to get the bridge sensitivity in terms of current sensitivity. And here also coming to the D, we are also checking for equal arms. If the arms are equal, R3 equal to R4 will be equal to R1 will be equal to R. Of course, here we have only R3, R4, that will be equal to capital R. So at that point of time, if that is substituted, you have SI into E into R square divided by R equivalent plus RG into 4R square. So R square gets cancelled out. You will be left out with SI E divided by 4 into R equivalent plus RG. So this will be the expression for bridge sensitivity whenever we have equal arms in the bridge. That is, when all the four resistances in the bridge circuit are equal to R, then this you will be getting this SP. So this finishes with Wheatstone bridge sensitivity expressions. Next, we'll talk about limitations of Wheatstone bridge. This bridge is not suitable for measuring resistances higher than the order of 0.1 mega ohms. We very well know this because it's a bridge suitable for measuring medium resistances. Next one, there is a heating effect due to the flow of large current in the arms of the bridge. So because of the large current flowing in the arms of the bridge, obviously there will be heat dissipation. Third one, leakage over the insulation may occur when measuring high resistance. Whenever you are trying to measure high resistance, it will be influenced by a large voltage impact. So there are chances for failure of the insulation between the arms. Then fourth one, this bridge is not suitable for measurement of low resistance below 1 ohm as the resistance of the leads and bridge contacts introduce errors. So here this particular bridge is neither useful for measuring low resistance nor useful for measuring high resistance. So both these are the two disadvantages. Then here in the last line he says resistances of the leads and bridge contacts introduce errors whenever you are trying to measure low resistance. So that itself will lead us to the next bridge, which is Kelvin's double bridge for measuring low resistance. So next topic now that we'll be seeing is measurement of low resistance using Kelvin's double bridge. So Kelvin's double bridge, there is nothing special. We are just going to modify the Wheatstone bridge in order to overcome the limitations of Wheatstone bridge. That's the last one disadvantage that we were talking about is nothing but measurement of low resistance is not possible because of resistance of lead and bridge contacts. So we'll just try to modify Wheatstone bridge such that it can measure low resistance. That the modification itself will bring in the same bridge in order to measure the low resistance, and the name given is Kelvin's double bridge. And of course the other parameters, this bridge is used for the measurement of resistance below 1 ohm with accuracy plus or minus 0.05% to plus or minus 0.2%. So for now we'll have to talk about lead resistance and contact resistance. Lead is nothing but terminal of the component. Suppose you are having a resistor along with you. The resistor has two leads on either sides for connecting purpose. It has two ends on either sides. The two ends of the resistor basically are called as leads. So those leads also contain some amount of minimum resistance. They also have some minimum resistance, that is called lead resistance. Another one is contact resistance, where whenever you try to connect two resistances together, the point of contact wherever you are connecting, that also introduces some additional resistance. So both these lead resistance and contact resistance will introduce error when you're trying to measure the parameters in the bridge, because other than R1, R2, R3, R4, these resistances also will be there. They will get added up to the actual resistances, because of which error will be introduced. So let us see how to overcome. So in order to overcome them, we have to first take them into account, and they arrive at some expression where we achieve the bridge balance, having them also into account. So in order to account for these contact and lead resistances, we are going to include two or three resistances to account for these. Let us see how it will be done. So now let us go for bridge balance condition. So if you just observe this particular bridge circuit, other than the actual Wheatstone bridge circuit, you are able to see resistance A and resistance B over here. So you are able to see resistance A, resistance B, and you are able to see Ry between node 1 and node 2. So here, instead of naming the nodes as ABCD, we have named it with numbers 6, 5, 4, 3, 2, 1, and galvanometer is connected between 5 and 3. And A, B, and Ry have been introduced to take it into account the contact and lead resistance. So let us see here. R1 and R2, as usual, they are ratio arms. Small a, b represents the lead resistance. I told you the resistance present in the end terminal of each and every component is the lead resistance. They are represented by A and B. And then you have Ry, which represents the contact resistance. Whenever you are bringing any two or three resistances in contact, that is, whenever you are connecting them in series or parallel, when there is an interconnection, it will introduce additional resistance, that is nothing but represented by Ry. Rx is nothing but unknown resistance. R3 is nothing but the standard resistance that we are going to use over here. Now, whenever you are selecting the resistances A and B, you will select them in such a way that A by B is always equal to R1 by R2. That is how you are going to select A and B. Already R1 and R2 ratio arms will be known to us. Their ratio should be equal to the ratio of A by B. That is how we are going to select A and B. Now, in order to derive the bridge balance condition, under balance we very well know that Ig is equal to 0. So when Ig is 0, V phi 3 will be 0. There won't be any potential difference if there is no current flowing through them. So V phi 3 will be 0. So we'll be applying KVL in the loop 6, 5, 3, 1, 6. I'm showing in the mouse here 6, 5, 3, 1, 6. In this loop, we are going to apply KVL, Kirchhoff's voltage law. So if you apply Kirchhoff's voltage law, you'll be getting I1 R2 plus V phi 3 minus this part V13 plus IR3 minus of V13 plus IR3. IR3 is nothing but current that is in this particular arm. Potential difference across 1, 3 is nothing but V13. So if you add them all, you will be getting 0 as per KVL. This is nothing but your second equation. So if you have a look here, V phi 3 is 0 because we are assuming the bridge is balanced. So V phi 3 is 0. So you will be left out with I1 R2 is equal to V13 plus I R3, capital I into R3. We have assumed capital I as the current flowing through R3 and small I1 as the current flowing through R2, as you can see in the circuit. So I1 R2 is equal to V13 plus I R3. So we have some simplifications to be made, some substitutions to be made. So we deal with LHS and RHS separately over here. First, let me take up LHS, I1 into R2. So I1 can be expressed as E divided by R1 plus R2, as we did yesterday. E divided by R1 plus R2 is I1. That will be multiplied by R2. So R2 by R1 plus R2 multiplied by E. E again can be expressed. So if you have a look at the equivalent circuit, a part of the circuit on the right side, you can see that we have A, B, and Ry connected in parallel. So if you try to write the expression for E, you will have R3 plus Rx plus Ry into A plus B by Ry plus A plus B. Because if you redraw the circuit in this manner, A and B will be basically appearing in parallel with Ry. So if you want to write the expression for V13, you will be using voltage divider rule here. So this V13 will be equal to V12 into B by A plus B. This is the expression for V13. So once you have the expression for V13, you can also write the expression for V12. V12 will be equal to current multiplied by the equivalent resistance. So equivalent resistance is nothing but parallel combination of A plus B and Ry. So Ry into A plus B by Ry plus A plus B multiplied by current will give you V12. So this V12 I am going to substitute in the expression that we have written for V13. So if that is done, your V13 will be equal to IB by A plus B into Ry plus A plus B by Ry plus A plus B. So A plus B gets cancelled. You will be left out with IB Ry by Ry plus A plus B. Further, I'll continue with RHS. IBRY by RY plus A plus B plus IR3. Let's go back to the previous case. So you can see in the RHS, V13 plus I into R3. This V13, I've got it from here. Whatever I have got till now, plus IR3. Further, let us continue with the RHS. So we'll take I as common factor. You'll be left out with BRY by RY plus A plus B plus R3. Now I'll bring back LHS and RHS, equate them. So if you refer to this, you have your LHS R2 by R1 plus R2 into I multiplied by R3 plus RX plus RY into A plus B by RY plus A plus B, because we have a parallel combination of RY and A plus B that will be appearing in series with R3 and RX. That when multiplied with I will give you the voltage multiplied by the resistance connected in parallel here, that will give you E. So if you just observe, between 6 and 4 we have R3, we have RX, we have parallel combination of RY, A and B. So R3 plus RX plus this parallel combination, that is RY into A plus B by RY plus A plus B multiplied by the current will give you the drop across this. That when multiplied by R2 by R1 plus R2, that will give us LHS. So this LHS and RHS now we are trying to equate. So if you equate LHS, this is the uh, LHS and this is your RHS. So if you take I as common factor in the RHS, if they'll get cancelled out, you'll be left out with R3 plus RX plus RY into A plus B by RY plus A plus B, and I'm transferring R2 by R1 plus R2 to the right side. So I have R1 plus R2 by R2 multiplied by R3 plus BRY by RY plus A plus B. Now in the next step, what I'm doing is I'll just take R1 by R2. I'm splitting this expression. So I have R1 plus R2 plus 1 multiplied by R3 plus BRY by RY plus A plus B. Now I'll be substituting equation 1 in the above expression. Let us go back and see what is equation number 1. So equation number 1 was A by B is equal to R1 by R2. So in place of R1 by R2, I can use A by B, or if there is A by B, I have to use R1 by R2. So over here I have R1 by R2. So in place of R1 by R2, I use A by B. So R3 plus RX plus RY into A plus B by RY plus A plus B is equal to A by B plus 1 multiplied by the remaining term. Now here if you expand this, you have R3 plus RX plus RY into A plus B by RY plus A plus B is equal to A by B R3. I'm just multiplying them. A by B R3, then A RY by RY plus A plus B plus R3 plus BRY by RY plus A plus B. So just multiplied them. Now R3 gets cancelled on both the sides. I am left out with Rx, which is equal to A by B R3 plus ARY by RY plus A plus B plus BRY by RY plus A plus B minus the term that is transferred from LHS is RY into A plus B by RY plus A plus B. So here, if you simplify them, the other two terms get cancelled out. You'll be left out with Rx is equal to A by B into R3. So from this, what we can understand again, Rx is equal to A by B R3, or it is nothing but Rxb is equal to A R3. So Rxb is equal to A into R3. So that is nothing but the bridge balance condition for Kelvin's double bridge circuit. So now here again, in place of A by B, I can write it as R1 by R2 from expression 1. So if I do that, R1 by R2 into R3 is equal to Rx. So from this you can understand that again we have the same thing, product of opposite resistances are equal. You can just observe the circuit, R1 R3 is equal to R2 into Rx. So R1 R3 is equal to R2 into Rx will give us the bridge balance condition. So this finishes with Kelvin's double bridge. So Kelvin's double bridge for measuring the low resistance value. Next topic is measurement of earth resistance. So first of all, we have to understand the what is the process of earthing. Then what do we understand by earth electrode? Then we'll go for measurement of earth resistance. So whenever it comes to earthing, you can go through the standard definition here. It is the process of providing an alternate path to the flow of fault current or excessive current safely into the ground. So whenever there is a fault current due to either short circuit fault or any kind of fault in the system, generally the fault current has to safely pass to the ground. It should neither damage the equipment or the human being who is working along with the equipment. So it should safely pass to the ground. So we'll have to provide the safest path. Safest path is nothing but the least resistance path you'll have to provide so that it safely reaches the ground without harming the equipment or the human being. So that is nothing but earthing. So the connection of electrical or electronic equipment to the general mass of earth with a conducting material of very low resistance is called earthing. So either of these definitions you can write down in the examination. Next, that particular conducting material that you are going to use is called as earth electrode. So let's see the definition. Conducting material used for earthing is called earth electrode. Resistance of the earth electrode is called earth resistance, and that has to be measured. Always we should see to that earth resistance we should be as least as possible. So in case the earthing is faulty, there may be chances that this resistance might have increased. So we should always try to monitor the earth resistance. So the effective earth resistance should be very low value. That's what is mentioned here. And this earth resistance, that is the resistance of that conducting material, depends on following factors: shape and material of the electrode. What is the shape of the electrode, whether it is cylindrical in shape or whether it is rectangular in shape, that matters. As well as the material of the electrode, what material you have you used copper or have you used aluminum, that matters. Second factor is depth of burial of the electrode. How deep you have buried the electrode also matters. Specific resistance of the soil. Specific resistance of the soil basically refers to the moisture content in the soil, and then where exactly you are trying to do it, whether you are doing it in a dry area or in a wet region or in a snowy region. It will vary from place to place, and it will also change from season to season, whether you are doing it in winter or monsoon or summer. That also matters. At the same time, the place where you are doing the earthing, all these factors will contribute to the specific resistance of the soil. So ultimately, the resistance of the earth electrode will depend on shape and material of the electrode, how deep it is being buried, and specific resistance of the soil. So a small value is given here. Moist soil has a specific resistance of 80 into 10 to the power of 3 ohm meter. So while the dry soil has 80 into 10 to the power of 6 ohm meter. Okay, this is just a statistic value that is given. So the dissolved salts in the soil will reduce reduce the resistance by around 8%, of course. Now here we will be seeing two methods for measuring this earth resistance. First method is fall of potential method. Second one is by using the instrument Megger. So in today's session, let us see fall of potential method, and further we'll be continuing in the next class. So coming to the fall of potential method, here this is the actual arrangement of the fall of potential method. It is called as constructional arrangement, as you can see. So let us see what this arrangement basically gives. Over here, the earth electrode E, whatever you are seeing here, is basically the earth electrode, which is the conducting material. A and B are auxiliary electrodes or supportive electrodes. You can say auxiliary means supportive electrode for conduction of this particular procedure. Capital I is nothing but the current flowing in the circuit. X and Y are the test points that are there in the ground in order to go for actual reference. And we have a battery which acts as a DC source. We have an ammeter to track the current, and you have voltmeter for the measurement of voltage. So this is the overall arrangement. Same thing you can see it has been described here. You can read the description later. Let us go to the operating principle. So initially, the battery is turned on and current starts to flow through the entire circuit. And once the current starts to flow, the potential difference is measured between the points E and A over here. That is between E and A, the potential difference will be measured and that will be shown in the voltmeter. That is nothing but VEA. And if you try to calculate the resistance, RE will be given by VEA divided by current I as per Ohm's law. So this will give you earth resistance value. Now the current flowing in the earth diverges from E and converges at B. As you can see in this diagram, current diverges from E and converges at B. So the current density is basically high near the surface of the electrodes. Current flowing in the earth basically diverges from E and converges at B. So the current density is high near the surface of the electrode. And then electrode A is basically placed between E and B. As you can see, this electrode A is placed at different regions over here. See, E and B position is always fixed, but the position of A will continuously be changed. It sometimes it is placed near E, it's near X, in between X and Y, near B. Likewise, at different positions, A is placed, and accordingly, the resistance will be measured. Voltage and resistance both will be measured. So if you do that, you can observe that the potential basically rises near the surface of the electrodes and remains constant between the points X and Y. So what basically happens here is when you try to measure voltage VEA by keeping this A at different positions in between E and B, we can observe that you can see the graph here. The voltage generally rises whenever the position of A is close to E as well as close to B, and remains constant whenever it is between X and Y. So from this what you can understand is whenever this A is placed in the center or away from the electrodes, the voltage remains constant. Whenever it is brought closer to B or closer to E, the potential rises. If the potential rises automatically, since the current is constant, resistance also is going to change. So that we are seeing in this particular graph. The resistance remains constant whenever the test electrode is placed between X and Y, and whenever it is placed near the electrodes, the resistance also is going to increase. So from this what we can understand is in the first line itself we have understood how to measure the resistance. We'll be measuring VEA divided by I, that will give you earth resistance. So far what we have talked is where does it give accuracy. When you're trying to measure that earth resistance, if you place it in the center between the two extreme electrodes, then only it will give you accuracy. If you try to place it near the electrodes, the potential and the resistance will rise and it will not give a constant value. The best place that you'll have to place them is in the center. When you place it in the center, it will give you accurate reading. So this will be the accurate position. So from this we can understand that VEA, that is voltage measured between earth electrode E and the auxiliary electrode A, will give us VEA. That one divided by current will give us earth resistance. And whenever you place this A almost at the center between the two electrodes, then the reading will be accurate. Otherwise, you will be seeing sharp rise in resistance value and the value will not be accurate. So this is called as fall of potential method. It is called as fall of potential method because the potential keeps falling or reducing as and when you take it away from the electrodes. That's why it's called as fall of potential method, to track the exact or accurate reading of earth resistance. So this finishes with the first method of measurement of earth resistance. So further I'll be continuing in the next session.